Okay, let's review limits from last year. Hopefully you had a chance to look at limits, and you're going to have a better chance to look at them a little bit more in depth this year. And the question is, which one of these has a limit as x approaches 1 that does not exist? In other words, there is no limit. So the easiest way to do that is to grab your pencil and trace the graph as x gets closer and closer to 1 from both sides of the graph. And what you're looking at is seeing if those two arrows match up, which in this case they do. So in this case, choice A, the limit does exist as x approaches 1. So it's not what we're looking for. So let's look at B. Again, trace it from as x approaches 1 from both sides. And you can see that even though there's a hole there, the graph still matches up on both sides of the graph. So the limit does exist. Let's go for D for a second here. And again, it's another one that has a hole in it. But if you notice here, when I trace it from both sides of the graph, the limit exists because, again, both sides are approaching the same value. Okay, so let's look at C now. Well, this one, notice here, when I approach it from the left side, as x approaches 1, and from the right side, you can see that they are not going to the same value. So this is the graph that the limit does not exist. So my correct answer here is C. Okay, so again, same graphs actually, but now we're going to look and say which of the following has a limit of x as x approaches 1 of f of x equal to 1. And again, if you look at this and trace it from both sides as x approaches 1, we're looking at the y value that we're getting closer and closer to. So in this case, hey, x does approach 1 from both sides of the graph. So choice A is one of our choices. Okay, now we look at B. You notice, again, we trace from both sides, but in this case, it gets closer and closer to the y value of 2. So this is not what we're looking for. We had looked at from the previous example that C is a graph in which the limit does not exist, so we know that can't be the answer. But if we look at D now, again, tracing from both sides, we can see that the graph as x approaches 1 actually approaches the y value 1. And the y value is 1. So again, in this case, there's actually two graphs that have the same answer. Okay, so let's take a look at C, for example, because this is the one, remember, the limit does not exist. We're going to introduce some notation here to show that what are the criteria for a limit to not exist. So if you notice, remember here, when we traced the left side of the graph, which is what we call the left-hand limit, we're going to denote that with a little negative symbol there of f of x. We saw that it was a little bit different than the right-hand limit, which we denote with a little positive symbol. These are both what we call one-side limits. Those limits, if you notice, exist. Remember, this was equal to 1, and the right-hand limit was equal to 0. And since these are not equal to one another, we then said that the limit as x approached 1, notice no positive negative symbol, so we're looking at the whole limit, we actually say equals d and e that does not exist. Okay, so let's learn how to determine limits algebraically. The easiest way to do limits is to do simple substitution. And you should always do that first, actually. Replace the x with the value that you're trying to find the limit for. So 4 squared minus 5 times 4 minus 4 equals negative 8. And so that is what the limit here. Real simple to substitute. Let's take a look at the next problem now. However, here, when we substitute here x approached 4 for every value of x, you'll notice here that we'll actually get 0 divided by 0, which is what is called an indeterminate form. And that form, it means that there is an answer. We can't determine it this way. So 0 divided by 0 means there's still an answer. We just got to look for a different way to find that answer. So to find that answer, the easiest thing to do is usually by factoring. Okay, remember your generic rectangles from Algebra 1. You do this by factoring. And so if you notice, the top factors to x minus 4 times x plus 9 over, we still have x minus 4 in the denominator. You may notice now the x minus 4's cancel. So we can find the limit by replacing our x equals 4 into our function. So 4 plus 9 equals 13. Okay, so if you look at this problem, limit as x approaches negative 2, you'll notice here that when I replace negative 2 in for both the numerator and the denominator, I actually will get 0 divided by 0, which is a form that means that there is an answer. We just can't find the answer by substitution. We've got to find it some other way. So we're going to use our generic rectangle to actually find the answer to this. And so I'm going to put the x plus 2 across the sides, and I'm going to try to figure out what goes inside here. So if you notice, this is the completed generic rectangle, and I filled in all the inner parts, and I found that the other side is x squared minus 5x minus 2. So that means that if I look at my original problem, the x cubed, which is in the numerator, that whole long equation divided by x plus 2 turns out to be this. And so now I can find the limit as x approaches negative 2 by substituting into that equation. So negative 2 squared minus 5 times negative 2 plus 2 will give me my answer. And this answer comes out to be 16. So this is how I would find my limit using the generic rectangles that you learned about last year. This last problem here is actually one that can be done with substitution. If I replace x with negative 2, if you notice here, I'll get 13 over 3, and that is not a problem. There's no dividing by 0 problem, so this is my final answer, so I can always use substitution. So that's the reason why we use substitution as the first way to solve every one of these problems, because many times it will work. But like in the problem above, sometimes it doesn't work, and we've got to try something else.